Next kind of flip-flop is the toggle flip-flop. I just told you because for the counter designing purpose, we need to keep either J and K both 0 or J and K both 1. 0 and 1, 1, 0 combination is not required in this case, especially on the counter designing side. Okay. So what it means? It means that both the inputs should be at the same logic. Either it should be 0 or it should be 1. So for that purpose, what we can do? We can simply connect J and K to the same logic, and that will become the, suppose, yeah, this is the JK flip-flop, where we have two inputs J and K and the two output Q and the Q bar. Okay, and if it is like that, and I just told you, because for the counter designing purpose, we need the toggle state where I can keep both the inputs either at 0 or 1. So if it is like that, considering this thing in our mind, we simply need to connect both the input at the same logic without inverter. If you can recall the D flip-flop, in that D flip-flop, we need one inverter. But here we do not need any inverter. Okay, we don't need any inverter. And if we don't need any inverter, directly we need to connect both the inputs. And this will become the T input. And here we will have a two output QT and the QT complement. So this is how the toggle flip-flop can be made with the help of JK flip-flop. Okay. Right. So this, yeah, so the resultant block diagram for the T flip-flop will look like this one. So this block, what we have made here, is nothing but this is the T flip-flop. Okay, this is the T flip-flop. Now let us try to analyze this T flip-flop, how this T flip-flop works, and how we can get it. So let us try to get the characteristics table of this one. Okay. One more important thing, if we can somehow recall the previous state in the SR latch, okay, the characteristics table was dependent on the Q, N, S, and R. So the total, the possibilities were eight possibilities were there. If you talk about a D flip-flop, so it was dependent on the Q, N, and D, and then we had only 4 possibilities. Okay, and if you talk about a JK flip-flop, so we had a combination like QN and the J and K. So in that case, we had a 8 combination in the characteristics table. And similarly, just like, because see, if we can recall all these things, if the number of inputs are 2, okay, so the total possible combinations like what we can make in the characteristics table are just like the total possible combination, yeah, total combination is equal to 2 to the power n plus 1. So this is really very important. Here n is the number of input in that flip-flop. If the number of input is equal to 1, so 1 plus 1, like 2 to the power 2 is equal to 4. So the total possible combination will be 4. If the number of inputs are 2, then the total combination will be 8. Okay, so this is the important formula that you need to consider, how many possible combinations we can make with the help of any flip-flop, and that is 2 to the power n plus 1. This kind of questions may come in the GATE examination. So this is important thing. Okay, so similarly, like, because in the T flip-flop we have only one input, so by default I will get only 4 possibilities. Okay, so in the characteristics table of T flip-flop, the total possibility, D and T flip-flop, the total possibility will be 4. So I need to make the characteristics table with only 4 possibilities. What are those possibilities? Those possibilities could be 0, 0, 0, 1, 1, 0, and 1, 1. Okay, these are the possibilities. Now let us try to see. This is what we have already done it. I know that if the T was 0, okay, in the JK flip-flop, let me go back to this slide here, somewhere here. So if you can recall, if the J and K was 0, so it was maintaining the same QT. And if J and K was 1, it was maintaining the QT complement. Okay, so because if we talk about the T, T flip-flop, these both are joined together. J and T are same, J and K are same, and that becomes a T. So I need to consider, like, if 0, 0, like if T is equal to 0, QT plus 1 will become the same as the QT. And if the T is equal to 1, it will become the complementary of the QT. Okay. So considering these things, let us try to see here. If T is equal to 0, what it means? It means that J is equal to 0, K is equal to 0. Okay. And if J is equal to 0, K is equal to 0, it maintains the same logic. QT plus 1, that will reflect the same. Okay. So this will become 0. Again, I will get the whatever the, like here I have the T is equal to 1. So J and K both are 1. So I will get the complementary of the input, like QT. So that will become 1. If 0, so it will be same like the QT, which is the 1. And if it is T is equal to 1, then it will complement the previous input. So it will become 0. So let me repeat it again, what I'm doing here. Let us try to see the first case. In the first case, the T was 0. T was 0 means this is same like J and K both are 0. Okay. And if J and K both are 0, so I know that Qn plus 1 for JK flip-flop is just like Qn. Okay. For J is equal to K is equal to 0. And for J is equal to K is equal to 1, the Qn plus 1 was like Qn complement. Okay. So this was the relation before. So now let us try to see here. In the first case, I will get this one, like the Qn plus 1 will be same like the Q1, Qn, or the Qt. N means T, Qt plus 1. Okay. It will be same like this one. Okay. So I need to maintain all these things. So accordingly, we can make the table. So it will toggle during this, during this case, this case. So this is how it can be made. So you just simply need to check the truth table or the characteristics table for the JK flip-flop, and accordingly you can make what will be the characteristics table for this one. Okay. So if T is equal to 0, it will maintain the same logic. If T is equal to 1, it will toggle. So the toggling are at two states, at this one and at this one. So these two are the states where the outputs will be toggled, or it will flip the logic as compared to the previous state. Okay. So this is important point of consideration here. Now let us try to, yeah, so by default the Qt plus 1 complement will be like 1, 0, 0 and 1. Yeah. Let us try to make the KMF for T plus Qt plus 1. Okay. So the KMF for Qt plus 1 will be simply like Qt and T will be there, and Qt plus 1 will be something like here. If you see, that will become the 0, 1, 1, 0. And if you see this expression, because we have a diagonal one over here, so this looks like a XOR kind of function. Okay, so we have a XOR kind of logic, and whatever the Qt plus 1 expression I will get, that will be the XOR, like Qt and the T will be XOR. Okay, so the output or the expression will be looking like this one, like Qt plus 1 is nothing but this is the XORing of this one, like simply Qt XOR T. Okay, so this is the expression, and this is what we call it the characteristics equation of T flip-flop. Okay. Now let us try to make some other things. Okay. If we know the characteristics table, we need to also make the state diagram. Okay. So state diagram, how the state diagram of the T flip-flop can be made with the help of characteristics table. So let us try to make the state diagram. Yes, again, we can have a two possibilities for our outputs. Either the output could be 0 or output could be 1. If the Qt are 0 or 1, in that case, we have a possibility. So let us try to see. If the qt is equal to 0 and t is equal to 0, yeah, so let me change the color first. Okay, so if the qt is equal to 0 and t is equal to 0, then the qt plus 1 is going to be 0. Okay, so the first state is this one, where I need to say this is nothing but this is equal to t is equal to 0. For t is equal to 0, I will get the same output. Now let us talk about the second case. If qt is equal to 0 and t is equal to 1, in that case qt plus 1 is going to become 1. Okay, so the output is changing its state from 0 to 1, and that is like 0 to 1, and the case is t is equal to 1. Okay, if we talk about the third case, in the third case, let us consider the qt was 1 and the t is equal to 0. So the qt was 1 here, t is equal to 0, then I was getting the same output. I will get the same output if again t is equal to 0. And for the last one, if the qt is equal to 1 and the t is equal to 0, in that case it is going to change from one state to another one, but it means that t is going to become 1. Okay, so this is how we can make the state diagram for this flip-flop. Okay, so this is also very important thing that need to be considered. Fine. Based on this, once we are ready with this state diagram, we can also make the excitation table based on the output characteristics in the whatever the qt and qt plus 1 we have. So let us try to make the excitation table for the t flip-flop. The excitation table will depend on qt and the qt plus 1. So if you see here, simply that from the state diagram we can make the excitation table. Okay, so I can have four possibilities based on the qt and qt plus 1. There is a possibility like qt is equal to 0 and qt plus 1 is also 0. This is 0, this becomes 1, 1 0 and 1 1. So these are the four possibilities. If we have the possibility something like this, what t we are getting? So let us try to see here. qt was 0 and the qt plus 1 was 0. So this loop indicates this case. The first case is indicated by this case, and we can see here at this state t is nothing but it is 0. If we talk about the second case, where the t is equal to 0 and the qt is equal to 0 and qt plus 1 is equal to 1. So 0 to 1, we are switching from here to here. In this case, t is going to become 1. Now let us talk about the third case. In the third case, where we are providing the qt is equal to 1 and the qt plus 1 is equal to 0. Okay, so if the qt is equal to 1 and qt plus 1 is equal to 0, what it means? We are considering this particular loop. This loop is considered. If this loop is considered, what it means? We need to have a t is equal to 1. Okay, and again for 1 1, this loop will work and the t is equal to 0 will be there. So this is how the excitation table for t flip-flop will look like.